Let's dive right into this explainer. Today, we're going to demystify chemical thermodynamics by treating the universe's energy just like something we're all intimately familiar with. Yup, a personal bank account. When you really think about it, nature is the ultimate accountant, right? It meticulously keeps track of every single transfer, every deposit, and every withdrawal of energy. We're going to build our knowledge block by block today. We'll start by defining the universe, then look at the properties of a system, introduce the currencies of heat, work, and energy, lock down the first law, and finally, end with a really powerful accounting tool known as enthalpy. All right, let's hit Section 1, defining the universe and the boundaries of thermodynamics. Now, the formal definition of thermodynamics, the study of different forms of energy and their quantitative relationships, might sound a bit intimidating at first. But what it really means, at its core, is that we're simply tracking how energy moves and changes forms in our physical world. It is literally the ultimate audit of nature. To make this audit possible, scientists split reality into two distinct parts. You've got the system, which is just the specific part of the universe we're observing. Think of a beaker of chemicals on a desk or a balloon filled with gas. And then the surroundings are, well, literally everything else interacting with it. The desk, the air in the room, the rest of the planet. So put them together, and the system plus the surroundings equals the entire universe. It's actually really fascinating to think about the different types of systems we encounter. Take open systems, like a completely unsealed beaker. They freely share both matter and energy with their surroundings. Then you've got closed systems, which can exchange energy in the form of heat, but they've got a lid on so no matter escapes. And finally, there are isolated systems, like a perfectly insulated thermos flask, that stubbornly refuse to share absolutely anything, neither matter nor energy, with the outside world.
Moving on to Section 2, Properties of a System, specifically intensive versus extensive properties.
The crucial point here is distinguishing between these two main types of properties. We've got extensive properties, and these absolutely depend on the quantity of matter you have. Think about mass or volume. If you pour more water into a glass, obviously the mass and volume go up. But on the flip side, we have intensive properties, like temperature or pressure. These stay exactly the same no matter the amount of stuff you have. Whether you're looking at a tiny cup of boiling water or a giant vat of boiling water, that intensive property, the temperature of 100 degrees Celsius, is exactly the same. And that brings us to a massive concept in thermodynamics, the state function. You can think of a state function exactly like your altitude on a mountain. If you're standing at the summit at 10,000 feet, it honestly doesn't matter if you spent 3 grueling days hiking up winding trails or if you just took a quick 5-minute helicopter ride. Your final elevation measurement, your state, is identical. In our energy bank account, we care heavily about the current balance, not necessarily the complicated history of every single transaction that got you there.
Okay, on to Section 3, heat, work, and energy. Basically, the currencies of thermodynamics.
Every single system has what we call an internal energy, and we represent that with the letter U. Think of this as the baseline account balance that contains all the stored energy of its molecules. This includes the kinetic energy of the molecules just buzzing around, the potential energy of their bonds, the chemical energy. It's all tallied up into one master ledger balance.
But, a bank account isn't very interesting unless there are actual transactions happening, right? Which naturally leads us to ask, how do we actually alter a system's internal energy balance? How exactly do we make a deposit or withdrawal?
Well, there are two main ways to make those transactions: through heat, which we represent with the letter Q, and work, represented by the letter W. Heat is transferred in or out strictly because of a temperature difference between the system and its surroundings. Work, on the other hand, is the physical, mechanical effort. For example, if our system is a gas, it might be expanding outward and physically pushing a piston against external pressure. Section 4 time, the first law, which is basically the ultimate accounting rule. This is a profound, practically unbreakable truth of physical reality, the first law of thermodynamics. The total energy of an isolated system, or really the entire universe, remains absolutely constant. There's literally no way to magically create new energy, and you definitely can't erase it. It simply shifts from one form to another. It might go from chemical potential energy into heat, or maybe from heat into mechanical work. You can actually distill this monumental law into a beautifully simple equation. The change in your internal energy balance, which we call delta U, equals the heat added, Q, plus the work done, W. It is quite literally just adding up your deposits and your withdrawals to find your brand new balance. But just like real banking, sign conventions matter immensely here. Deposits into the system increase its energy, so they're mathematically positive. That means heat absorbed by the system is a positive Q, and work done on the system, like physically compressing it, is a positive W. Conversely, withdrawals are negative. If our system releases heat, that's a negative Q. If our system expands and actually expends effort to do work on its surroundings, it loses energy, making it a negative W.
And finally, Section 5, the power of enthalpy, or specialized thermodynamics.
So here's the thing. Most chemical reactions don't happen in rigid, sealed steel containers where the volume is completely locked. They happen in open beakers, sitting right there on lab benches, totally exposed to the constant atmospheric pressure of the room. Because of this, scientists came up with enthalpy, represented by H, to easily track the heat flow under these exact real-world open conditions. It essentially just bundles the internal energy mathematically together with the pressure-volume work.
What you should really take away from this is that it's a brilliant shortcut. If the pressure doesn't change, which is true for pretty much any reaction sitting open on a desk, calculating the seemingly complex enthalpy change is just a matter of measuring the heat transferred. Delta H equals Q at constant pressure. This makes the lives of chemists immensely easier. It literally allows them to measure heat changes with a simple thermometer and directly know the enthalpy change of the entire reaction.
And when we look at the atomicity of gases and their heat capacity ratios, we can see how thermodynamics perfectly categorizes the way different macroscopic molecules absorb this heat based on their degrees of freedom. For instance, a simple monatomic gas like helium absorbs and stores heat very differently than a complex triatomic gas like carbon dioxide. Carbon dioxide can vibrate and rotate in much more complex ways, which basically gives it way more places to store its energetic deposits. To wrap up our explainer today, I want you to consider this really fascinating reality. Your own human body is, strictly speaking, an open thermodynamic system. You are constantly radiating heat, you're doing mechanical work as you breathe and move, and you're taking in matter and chemical energy through your food. So what kind of energetic deposits and withdrawals are you continuously exchanging with the vast universe at this very second? Keep exploring, keep analyzing your energetic bank account, and we'll catch you in the next explainer.